Hello everyone, and welcome to the K-means clustering custom code along lecture. So we're going to be working through a real data set containing some data on 3 distinct seed types. And the corresponding notebook for this lecture is called Clustering Code Along, and you can find it under the clustering folder under Spark for Machine Learning of the Spark notes. So for certain machine learning algorithms, sometimes it's a good idea to actually scale your data. And this is due to something called cursive dimensionality, which you can read about in an introduction to statistical learning. But basically what happens is you have a drop in model performance with highly dimensional data. So we're going to get some practice scaling features using PySpark. While it may not be necessary for this particular data set that we work with, later on if you're dealing with a data set that has many features to it or many columns of data, which is highly dimensional, what you need to do is actually scale those features. So we'll show you how to do that with PySpark and get some practice. Now remember, there won't be any confusion matrix or classification test results when dealing with unsupervised learning, meaning we don't have the original labels to actually perform some sort of test against. And again, I keep mentioning this issue that it's a little hard to evaluate an unsupervised learning algorithm for truth because you never have those true labels to begin with. So this is a common point of confusion for beginners. You can't easily check to see how well your clustering algorithm performed, and this is a difficulty for all unsupervised tasks. And if this is something that is a confusing point for you, then I suggest you do the reading in an introduction to statistical learning that explains the unsupervised learning process and clustering algorithms in general. So let's get started. I'm going to open up a new Jupyter Notebook and walk you through the data as well as the process. Alright, started a new notebook, and the first thing I'm going to do is actually start a Spark session. So I'll do this quickly since we've done it so many times before. Spark session, builder, app name, and I'll just call this cluster. And then I'm going to get or create this Spark session. Now the next step is to explore the data and what it actually looks like. It's just a simple CSV data set. So we can say spark.read.csv. And this data set is called seeds_dataset.csv. And then we'll say header is true. And we'll also say infer schema is true. And now let's take a look at the dataset schema. So I'll say print schema. And we can see here we have various columns: area, perimeter, compactness, etc. So let me give you a little bit of background behind this dataset. So this is a seeds dataset, and it's obtained from the University of California Irvine Machine Learning Repository. And the link is in the notebook that corresponds to this lecture. And basically what this is an experiment in visualizing kernels and their actual features. So a group got some kernels for 3 different varieties of wheat. That is Kama, Rosa, and Canadian. And there were 70 elements each, and they randomly selected them for this experiment. And what they ended up doing was they created a really high quality visualization of the internal kernel, that is the seed structure, that was detected using an X-ray technique. So what they ended up doing is taking a bunch of geometric parameters using those X-ray pictures. So things like the area of the kernel, the perimeter of the kernel, the length, width, etc. So you have all these characteristics, and all of these values are just real valued continuous numbers. So if we take a look at what an example looks like, so if I say dataset head 1, notice here I have the area, perimeter, etc. They're all essentially just numbers. So these are all just features of those actual seed and kernels. Now, we don't have that many features or dimensions here, and actually they're all around the same magnitude. It's from 0 to maybe around 25-ish. So as far as scaling goes, it will probably not be necessary, but we're going to work through that anyways. Okay, so again, and one more thing to notice here is that there's no actual label indicating what seed belongs to what group. What I do know, however, is there was 3 different varieties of wheat. So what we're going to try to do is cluster this with k equals 3. And that's essentially where our domain knowledge comes into play. So maybe you're out with these experimenters, you're out in the field collecting samples, and through your domain knowledge, you know that there's 3 possible seed types to be found in this field. However, you don't know what seeds you collected or something, and you want to cluster them knowing with your domain knowledge into 3 separate groups. So that's kind of an example of using your domain knowledge. So we'll continue along here, and we'll say from pyspark.ml clustering import k-means. All right, Now what we're going to do is actually format the data. So we can say from PySpark.ml.feature import, and I need to import a vector assembler. And then if we take a look at the columns, remember that this is an unsupervised learning algorithm, and luckily I only have feature columns here. And this is a Python list, which is exactly what I would usually pass to my assembler object. So instead of the input column argument going to be a list, I will just pass in this dataset.columns object. So let me show you what I mean by that. I'm going to create my assembler, set it equal to vector assembler, and specify that the input calls argument is just going to be dataset.columns instead of having to copy and paste all that. And then finally, the next thing I want is my output column to be called features. So now we'll run that, and then the next thing I'm going to do is just transform this. So I'll have final data is equal to my assembler object, and then I'm going to transform my data set. And if I take a look at my final data and print the schema, I can see here it has these various columns, but more importantly, it has the features column. Now in the past, what we've done is just select this features column, but actually a lot of these machine learning algorithm objects, they don't mind having a bunch of extra columns. They won't read them in, they won't do anything with them. What they're really looking for is the features column or the label column. In this case, we don't need a label. We're really just needing that particular features column. So we'll just keep final data as is. And now what I want to do is work through the scaling of the data. So in order to scale the data, it's actually quite simple. We'll say from PySpark.ml, and under the feature family, we'll say import standard scaler. And then this is almost like creating an assembler object. We'll say scaler is equal to a standard scaler object, where we expect the input column to be equal to features, and we expect the output column to be equal to, and we'll call this, whoops, pass in a string here, we'll call this scaled features. And then there's other parameters here, and if you do Shift Tab over at standard scaler, you can explore them. But essentially what you can do is with mean or with standard deviation. So this essentially just describes how you actually want to do the scaling itself. So do you want to do it with the mean, or do you want to do it with the standard deviation? And you can actually check here the Wikipedia page in case you want more information about the background behind the mathematics behind that. We'll just keep the default. That should be fine for us. So we'll run that scalar object, and then we're going to fit that to the final data. So I'm going to make a scalar model variable, and that's going to be scalar fit on the final data. It's almost behaving just like a machine learning object. So you fit it to the final data, and then you transform the final data. So I'm going to overwrite my final data, and then say scalar model, and then transform my final data. And some people like to do this all in one step, so they put this dot transform right over here after the dot fit. I'm just doing it in two steps so you can get an idea of what's happening. So basically what is happening here is this scalar object, when you fit it to this final data, it collects that standard deviation information, and then it sets that into this scalar model. So the scalar model is then ready to collect anything in this form of final data, and now it can transform it to be scaled, which is what happens when you call transform. So that's kind of what these two steps are doing here. All right, so now let's actually take a look at what final data looks like. If we take a look at the head, notice we have our features column, and then we have our scaled features column. Now in this case, as I mentioned, everything seems to be around the same order of magnitude, so the scaling isn't going to be such a big deal here. So you can see that there is a change between the features and the scaled features, but it's not a huge change. This becomes more important when you have not just high dimensions of data, meaning many features, but you also have orders of magnitude varying a lot between your actual data. So maybe you have one column that's in units of thousands of miles or something, and then you have another column that's in units of millimeters. Those kind of things can also be improved upon using some sort of scaling technique. So hopefully by now you understand how to use scalar, even though we probably didn't really need it for this particular data set. So now it just comes time to train the model and try our best to evaluate it. So we'll say k-means is equal to an instance of k-means. Oops, there we go. And earlier we saw this method, the setK, but you could also provide it as a parameter. So if you do Shift Tab here, you can see here that it actually takes in a k value. So what we're going to do is the following. We'll specify that the features column is going to be the scaled features. So we'll say scaled features, and then we'll specify k is equal to 3, since we know we expect 3 seed groups. And then what we're going to do is actually create the model. So model is that k-means object, and we'll fit it to all the final data. And now, once this is done, we're basically done with the model. So what we can do is the following. We can say WSSSE for the within set sum of squared errors, and that's just equal to, well, we can actually print this. So we'll say print within set sum of squared errors, and then we will say the following. We'll say print the model, and we can compute the cost on that final data set. And so there's our within set sum of squared errors. Now this isn't super helpful because we scale the data, but just keep that in mind that you can access that information if you ever need to. If you're looking for the cluster centers, what you can end up doing is just saying centers is equal to model cluster centers, and then we can print the centers. And there you have it, some array, and we have, it's a little sloppy because I'm zoomed in here, but you can see here that in this 1, 2, 3, 4, 5, 6, 7 dimensional space or more, you can see the centers themselves. And there's 3 groups of centers, which makes sense because we set k equal to 3. Now what we really want to know probably is the actual predictions, and that's usually what you're most interested in. So we can grab those by saying model transform the final data, and then we're going to show the results here. So we have a bunch of columns here, so let's actually select the ones we're interested in. So we're going to say select, and we'll say prediction. And now I can see the prediction for each of the groups, and it's going to start indexing at 0, so the group possibilities for my prediction are either 0, 1, or 2. And that's basically it. As far as checking this against some labels, you can if you want to, because this particular data set from UCI, it did actually come with labels. I stripped those before we started, but in a realistic setting, you wouldn't have those labels. Otherwise, you wouldn't need to do clustering since the beginning. But hopefully this showed you how you can use k-means to discover clusters within your unlabeled data sets. Okay, coming up next is your consulting project. I think it should be a really fun one. There's a really cool premise behind it. So I'll see you in the next lecture.